This is part 11 of the series Integration, and in this section we're going to continue the use of the net change theorem, and we're going to apply it specifically to particle motion problems. When dealing with particle motion problems, there are two fundamental quantities that we're going to be concerned with. The first is displacement. Displacement is the net change in distance traveled, or it's the measurement of the particle's final position as measured from its initial starting point. So, for example, over here we have a particle that starts at position 0 and moves to the right 10 units. Then it turns around and moves to the left 2 units. And then it turns back around and moves to the right another 7 units. The particle's net change, or displacement, is the measurement of its current position from its initial starting point, which is 15 units. So the net change of this particle was 15 units, or the displacement is 15 units. The second quantity that we're concerned with is total distance. And just as it says, it's the sum of the distances the particle travels regardless of the direction. So in this case, if the particle moved 10 units to the right and then moved back to 8, that means it's moving 2 more units, so that's 12. And then it's moving another 7, so the total distance the particle traveled from its starting point through its entire path is 19 units. Relating this idea back to the net change theorem, we can find displacement on a closed interval AB by integrating the rate of change function on the interval AB. Let's say that this graph represents a rate of change function. And what we would do to find the displacement is we would add the area of this portion of the curve from here to here, from these two 0 points, to this area, and then we would subtract this area, because this area, of course, is a negative, so plus, minus, plus. So the area 1 minus area 2 plus area 3. And that would give us the net change of whatever that quantity is. Now, to look at total distance traveled, we'd have to do something slightly different. In this case, we don't want to subtract this because this basically represents going backward. So if the particle is moving forward and then it's moving backward and then forward, we actually want to add this plus this plus this. And the way to do that is we'd have to integrate across the absolute value of the function. So in essence, what we're doing is we're taking each lobe and making it positive. Something like this. We would take this piece and flip it, making it positive. That's what taking the absolute value would do. So we have no negative components. Now, obviously that's going to require a little bit of extra work because we'd have to find where this 0 and this 0 would be, and whatever other zeros we'd have, depending on the function we're integrating. And we would have to change our limits of integration accordingly to change the sign of this, because there's no real absolute value integral that we're going to be taking. This is just the idea that we're taking all positive values of the function and allowing no negatives. So let's try to work a problem and see how this applies. In this problem, we have a particle moving along a line, and the velocity function is given by this expression, and we're looking for the displacement of the particle on the time interval from 1 to 5 seconds. So that's all we really have to do here for displacement, is to take the definite integral. So for A, we want the integral from 1 to 5 of t to the third minus 10t squared plus 29t minus 20 dt. This yields us t t to the fourth over 4 minus 10t to the third over 3 plus 29t squared over 2 minus 20t evaluated from 1 to 5. Evaluating this expression at 5, at t is 5, gives us 25 twelfths minus, evaluating this expression at 1 gives us negative 103 twelfths, which simplifies to 128 twelfths, which is the same as 32 thirds. Now, my recommendation for these problems is once you've gotten to this point and you've shown this work on your paper, you will want to use your calculator to evaluate the integral. Especially if you're taking the AP exam, of course you follow all the instructions. Often on the AP exam, they'll ask for the integral, they'll ask for the answer. So you'll want to show this and then let the calculator tell you what the result is and put your result down in 4 decimal place accuracy. In case you're not familiar with the process of doing this in your calculator, and assuming that you have a TI-8384 family calculator, I'm going to go ahead and pull mine up and just show you really quickly how to do this. You'll want to turn the calculator on, go to y equals, and enter your expression using x for t. So x to the third minus 10x squared plus 29x minus 20. Now that's the function we're going to integrate, and we can do it in 2 ways. We're going to use the graph first, so we're going to do second calc. So you hit second trace. Trace is the calc button. And we're going to be using the integral down here. So it's option 7. It takes a couple seconds for the graph to be drawn. And then it asks for the lower limit. Our lower limit is 1. Enter. And then it asks for the upper limit, 5. Enter. And it goes ahead and calculates it, and there's your value. So, and as you can see, it comes out to be the same result as we got before. So that's a quick example of how to do this on your graphing calculator. When I say evaluate in your calculator, that's what I'm talking about. All right, let's move on now to part B. To evaluate part B, we're going to have to take the integral of the absolute value of the function. So this is going to look a little bit different. Rather than writing the whole thing out, I'm just going to say for part B, we want the integral from 1 to 5 of the absolute value of v of t dt. Now, in order to evaluate this, we're going to have to find the zeros of this function, because we're going to have to determine where this thing, if any place, it has positive or negative lobes. So the easiest way to do that is to, again, go back to your calculator and let your calculator tell you where the zeros are. Now, you're perfectly welcome to go ahead and use the rational zeros test to try and factor it using any of your pre-calculus methods, but my recommendation would be use the tools at your disposal, but exercise discretion. Don't use the calculator to do everything. We're going to show all of our work. We're just using the calculator to take care of the tedious details. We're not actually having the calculator do everything for us. So let's go ahead and bring back our calculator, and let's look for our zeros. Now we know one of the zeros is at 1, and that's our lower limit. We're concerned with this and this 0. So we'll go ahead and hit clear, get rid of the last result. Could do a second trace, and we're looking for the zeros, option 2. And we want to find this one, so we could either select the value over here like 2, or we could have used the arrows to move over. And then we need to go over here, and I'm not sure exactly where that's going to be, so let's just use the arrows. There we go. And we find a 0 at 4. So we have 1 0 at 4. Now let's look for the other one. And 1 at 5. So we know our zeros are at 4 and 5, which is nice and convenient. Now you can see that this is a negative lobe. So the one between 4 and 5 is the one we're going to have to change. So let's go back to our problem and work these zeros out. So using our zeros, we know that we're going to have an integral from 1 to 4 of the velocity function. And we're going to have another integral from 4 to 5 of the velocity function. Now the trick is, what sign goes in here? Well, we have to add them together. But remember, because we have this strange little negative lobe here, this area is going to come back negative. So if we want that to be a positive value, we're going to want to subtract that negative value. So we would subtract this integral. Now, the other way you could do it is we could have said equivalently that we could have added the integral from 5 to 4, because when we change the limits of integration, it changes the sign of our result. But either way you do it, it works out the same, so it's a matter of preference for you. So this is what we're going to do. And to evaluate this then, we're going to integrate from 1 to 4 of t to the third minus 10t squared plus 29t minus 20 dt minus the integral from 4 to 5 of t to the third minus 10t squared plus 29t minus 20 dt. That gives us t to the fourth over 4 minus 10t to the third over 3 plus 29t squared over 2 minus 20t evaluated from 1 to 4 minus the same thing evaluated from 4 to 5. So we're going to go back to our calculator to evaluate this, and we're going to use a slightly different method. We've already got our function in, so we're going to use that. So we do second quit to go back to the main screen. We're going to do math. We're going to go up to fn int, function integral. And then we're going to do vars, go over to yvars, press function, and select y1. That puts in the function. Then we put in the variable of integration, then our lower limit, and then our upper limit. So we're doing the integral of f of x from 1 to 4 minus, and then we're going to do that again, math, up to fn int, vars, yvars, function, y1, comma x, comma, now we're going from 4 to 5. And hit enter, and it gives us our value, 11.8333. And if you want to see if that has an exact translation, you do math, enter, enter, and it comes out to 71/6. So going back to our problem, the answer is 71/6. And now let's move on to the next section.